So we said that if you look at the periodic table, you guys, we said that the first group, group number one, which is the alkali metals, those they have the tendency to lose an electron. So this is why their sign is plus one, with the exception, of course, of the hydrogen. So lithium loses an electron and becomes lithium positive. Same thing, sodium loses an electron and becomes sodium positive. Potassium loses an electron. Rubidium also. Cesium as well. And the francium as well. Okay. Now group number two, which is here the alkali earth metals, we said that these have the tendency to lose two electrons. So beryllium loses two electrons and it becomes a 2 plus. Same thing for magnesium, it loses two electrons and become 2 plus in there. Same thing for calcium, it becomes 2 plus. Strontium as well, it becomes 2 plus. Barium as well, and radium as well. Okay. We're going to skip the transition elements because the transition elements have the tendency to lose more than one electron. It depends. For example, iron can lose two electrons. They can lose three electrons in there. So we're going to skip the transition elements, but we're going to come back to them in a later chapter in energy. So group number three here, boron, aluminum, gallium, indium, all of those, they do lose the three electrons. So again, a group number one, with the exception of the hydrogen, loses one electron. A group number two loses two electrons. A group number three loses three electrons. Now, group number four, it depends. So group number four can either lose four electrons, or is neutral, it has a zero sign, or it can gain four electrons. Okay, that is group number four. This is an exception. Now, coming to the nonmetals, group number five. Normally, nonmetals, they gain electrons, and gaining is represented by a negative sign. So the nitrogen over here, this is a group number five. The group number five gains three electrons. So that is going to be negative three because they gain three electrons. A group number six, which is the oxygen, the sulfur, this gains two electrons. So normally when we want to represent a nitrogen ion in there, we represent it as N minus 3. This is called a nitrogen ion. An oxygen ion is an O negative 2. Okay. Fluorine, chlorine, all of these halogens, this is a group number 7. So group number 7 normally gains one electron. So we represent the fluorine as an F minus in case of an ion. So if it's an ion, then it is an F minus. It's not an F plus, it's an F minus in there. And then the noble gases are in neutral. Noble gases neither gain nor lose. Okay, neither gain nor lose. So these are the charges of these elements in the periodic table. If they lose or gain, they become charged, and when they become charged, we call them an ion. Whether it's a plus a charge, positive charge ions, we call these cations, or negative charge ions, we call these anions. So you have cations, you have anions. Normally, cations are for metals, anions are for nonmetals, with the exception of the carbon family. Carbon family is made up of nonmetals in there, metalloid and metals. But the carbon family can either lose four electrons, gain four electrons, or have a zero charge. So to start with the arrangement of electrons around the nucleus, Bohr is a scientist who proposed that electrons in the elements, they do move around the nucleus. So we know that the nucleus is made up of what? Of protons, and it is made up of neutrons, right? And around the protons and the neutrons, you have what we call electrons in there. And these electrons, they do orbit around the nucleus. They do orbit around the nucleus. He proposed that they orbit in circular orbits. And electrons, they could change the orbits by simply absorbing or releasing energy. In fact, it was later discovered that these electrons, they don't rotate around the nucleus in circuit orbitals. They do move very fast around the nucleus. They do move very fast, but they move in elliptical orbits around the central nucleus. So instead of circular orbits, as I just said, the location and the energy of the electrons moving around the nucleus normally is specified within three terms: shell, subshell, and an atomic orbital. So let's have this model in there. So imagine over here that you do have the nucleus, and we said that the nucleus is made up of protons, and it is made up of neutrons in there. Okay, and then we have the electrons that go around the nucleus in an elliptical motion, but I'm not going to draw the elliptical motion, so I'm just going to show it like this. So how are electrons oriented around the nucleus? Electrons, they orbit the nucleus in shells, and these are the shells in there. So they rotate around the nucleus in shells, and the shells are 7 shells, starting from n equal to 1, which we're going to call it the K shell, and then n equal to 2, this is considered to be the L shell, n equal to 3, the M shell, n equal to 4, n equal to 5, n equal to 6, and then the last one is n equal to 7. Okay, so you have the K shell, we have the L shell, we have the M, the N, the O, the P, and the last one is going to be the Q shell in there. So we have 7 shells where electrons reside around the nucleus. Now, inside the shell, so here's what you have to imagine. We are explaining where the electrons are located around the nucleus. So around the nucleus, you do have shells, which are these 7 shells in there. Here I'm representing one of them, which is n equal to 4. Okay. Now the shell is made up of what? The shell is made up of subshells, and the subshells are made up of orbitals, and inside the orbitals we do have the electrons. So what are the subshells? The subshells are simply the S, the P, the D, and the F. We're going to define them in a moment in there. And the subshells are made up of orbitals. So for example, the S subshell is made up of one orbital, okay, and it has a capacity of 2 electrons. The P subshell is made up of 3 orbitals, and it has a capacity of 6 electrons. The D subshell is made up of 1, 2, 3, 4, and 5. 5 orbitals, and it has a capacity of 10 electrons. And the F subshell is made up of 7 orbitals, and it has a capacity of 14 electrons. So let's consider each one of these subshells. So starting with the S subshell in there. So the S subshell, it does appear as a circle. Okay, so the S subshell, if you take a look at it, it does appear as a circle like that. This is how it appears, and it is made up of one orbital. So this is the one orbital here, just one orbital. We normally represent the orbital as a box like that. So we represent the orbital as a box, and inside the orbital there is electrons there. It does have a capacity of a max of 2 electrons. And when you want to fit electrons in, you have to remember that you're fitting 2 electrons in one orbital. So these 2 electrons, they need to have opposite signs in order, or opposite orientation, so that they will not repel each other. So when I want to fit them, I'm going to start with the first electron being in the upward orientation, And then the second electron simply in an opposite orientation so that they have different spins there. So they would not repel each other. They would attract each other and they would stay in the same orbital. This is called Pauli exclusion principle. So what is Pauli exclusion principle? It just states the rules for electrons to be in the same orbital. They have to assume opposite orientation so that they will not repel each other. Okay. So this is for the S. Now the P subshell. The P subshell appears like a lobe, and whenever we want to draw a lobe, the lobe is drawn like that. Okay, so that is the P subshell, and it's made up of three orbitals. It's the px, the py, and the pz. And to represent those orbitals in there, we represent them as boxes that are connected to each other, so like that. Or you can represent them as circles. It's really, it doesn't matter. It's the p orbital in there. So each one of those is called a p orbital. Okay, so you have the px, you do have the py, and you have the pz. Always remember that every orbital has a capacity of 2 electrons, not more than that. Now, because the p orbital is made up, or p subshell is made up of 3 orbitals in there, whenever I want to fill them, I want to make sure that every orbital is filled. So I cannot fill one orbital to the capacity and go to the next orbital and fill that. It doesn't happen this way. The p subshell has a maximum capacity of 6 electrons. So it has a maximum capacity of 6 electrons. And the way that I fill those 6 electrons, I start with px having 1 electron, py having 1 electron, pz having 1 electron. Okay, I fill all the orbitals first, and then I still have 3 more, and then you go ahead and let's use another color, and you use an opposite orientation direction for the electron in there. Make sure that you satisfy the Pauli principle in order to fill the rest of the electrons, so that electrons, they will not repel each other. The p subshell, as I said, is made up of the px. The px is along the x-axis, the py is along the y-axis, and the pz is along the z-axis. It is a subshell that has a capacity of 6 electrons, and it is made up of 3 orbitals. We do care about the orbitals there because this is where the electrons reside. And then we have the d subshell. The d subshell appears like a butterfly, and it is made up of 5 orbitals. So draw the 5 boxes next to each other. It does have a maximum capacity of 10 electrons. And we're going to fill those exactly as we did in the P. So we're going to start having every orbital. This is 5 orbitals. So here I do have 5 d orbitals. This is 5 d orbitals. So every orbital is going to end up having 2 electrons, so that you have a maximum capacity of 10 electrons. You cannot fit more than 2 electrons in one orbital. But the way that you fill those orbitals, you start by filling them halfway, but you need to fill all of them halfway, and then you still have 5 more. So you're going to go ahead and follow the Pauli exclusion principle in there, so that electrons, they will not repel each other. They need to have different orientation, and this is the 10 electron d subshell. And then the F subshell. These are made up of 7 orbitals, meaning 7 boxes in there. Each box, or each orbital, has a capacity of 2 electrons. So you're going to end up having a maximum capacity for all the 7 orbitals to be 14 electrons there. So we're going to start filling them. This is 1, 2, 3, 4, 5, 6, 7. And then this is 1, 2, 3, 4, 5, 6, and 7. This is a total of 14. Valence electrons, what are these? These are electrons that are present in the outermost shell. So what is the outermost shell? The outermost shell differs from one element to the other. If you take a look at the nucleus and the shells around the nucleus in there, we said that these electrons, so this is the shell, and the electrons, they do reside in the orbitals in the shell, right? Now every element has a different outermost shell. So it does have, this is the outermost shell that has electrons. It has a different, so for example, some elements, they end up in n equal to 1 shell. So their outermost shell is n equal to 1. Some elements, they end up in n equal to 2 shell. They don't have electrons past that. So their outermost electrons are the ones that belong to the n equal to 2 shell in there. So these outermost electrons, we call them valence electrons. They belong to the outermost shell. It is the last shell of the element, okay? And these, they do correspond to the group number. It's easy to find them by simply knowing where the element is in the periodic table. So for example, lithium, if you can put the periodic table please next to you. Lithium is in a group number 1. So the valence electrons of lithium is going to be equal to the group number, and that is going to be equal to 1. It's important to know what is the valence electrons, because the valence electrons, these are the number of electrons that are present in the outermost shell. Magnesium is a group number 2, so the valence electrons for magnesium is 2. This means that it has 2 electrons in its outermost shell. Boron is in a group number 3, so it does have 3 electrons in its outermost shell. Carbon is 4, so it does have 4 electrons. Oxygen is group number 6, so it has 6 electrons. Nitrogen, it has 5 electrons because it's a group number 5. Boron, it does have 7 electrons, and the krypton, it has 8 electrons in its outermost shell, meaning that the outermost shell is filled. Okay, so let's relate this to the electronic configuration, you guys. So what is an electronic configuration? Electronic configuration is the electronic map of elements in the periodic table, and it's the representation of the electrons in an atom. And we said that we are starting with the nucleus, and the electrons, they do rotate around the nucleus in shells from n equal to 1 to n equal to 7 there. Okay, so we're going to start arranging them, because every shell here, it does have a subshell. Okay, so every cell, it is made up of a subshell, and the subshell is made up of orbital, and the orbital has the electrons in it. So we have the S, the P, the D, and where's that? The D and the F. All of those are considered to be subshells. And inside the subshells, we have orbitals. So the S subshell has the S orbital. The P subshell has the P orbital, and there are 3 P orbitals. The D subshell has 5 D orbitals, and the F subshell has 7 F orbitals. Okay, so n equal to 1. The first subshell is n equal to 1, has only the S orbital in it. That's it. It doesn't have any other orbitals. So that is n equal to 1. It does have 1 orbital, so we're going to go ahead and write it as 1s. See that arrangement here that you see? This, you can have that in the cheat sheet. And I've wrote this in the cheat sheet for you as well. Okay, so n equal to 1 has only the S orbital. N equal to 2 has the S orbitals, or the S subshell and the P subshell. N equal to 3 has the S, the P, the D. And n equal to 4 has the S, the P, the D, and the F. Notice all of those are n equal to 4. So n equal to 4 and 5 has the S, P, D, and F. And then n equal to 6 has the SP and D, and n equal to 7 has the SP. Please memorize or know this orientation, because you would need it in order to write down the sequence of the electronic configuration. So to write down the sequence of the electronic configuration, we are going to start with simply the 1s. So you start with the 1s in there, okay? Um, and let me take this one out and write it again. So you are starting with the 1s. See my arrow? That is the 1s. So now I'm writing the sequence of the electronic configuration. And then I have the 2s. And this sequence is always used, okay? And then I have the 2p and the 3s. You need to write them like this so that you can write them in the right sequence. So you have the 2p and the 3s. And then we have the 3p, the 4s. So this is the 3p and this is the 4s. And then we have the 3d, 4p, and 5s. So 3d, 4p, and 5s. And then the 4D, the 5P, and the 6S, 4D, 5P, and 6S, and then the 4F, the 5D, the 6P, and the 7S. So you write them like this, 5D, 6P, and 7S. And then the last is the 5F, and the 6D, and the 7P. Now it's time to fill the electrons, okay? So we know that the s orbital has a maximum capacity of 2 electrons. This is another s, it's 2 electrons. The p has a maximum capacity of 6. The s has a maximum capacity of 2. The p is 6, the s 2. The d is 10. The p is 6, the s is equal to 2. This is 10, this is 6, this is 2. F is 14. The D is 10, the P is 6, the S 2, the F is 14. So you have two F's in there. You have the 4F and you have the 5F. And then you have the 6D, which is 10, and the 7P, which is the 6. So this is the full sequence of the electronic configuration.